Hello everybody, thank you for joining us at the presentation of the DMX Protocol for discrete 3D fault and fracture modeling. I hope you will enjoy it. Let's start with the classical diagram showing the description and modeling of faulted and fractured reservoirs. On the left, we have static description and modeling. On the right, the dynamic description and modeling such as history matching. In this paper, we will be occupied with the static description and the construction of the conceptual geological model using the FMX suite and with the DMX protocol, which is occupied with the construction of three-dimensional discrete fault and fracture networks. The use of these networks is to extract properties, to look for the best direction of deviated and horizontal wells, to be transported to discrete flow models, to extract characteristics such as the effective block size, sigma factor, and to perform upscaling for reservoir modeling. So let's take a look at the complexities fault and fracture networks present in nature, because one of our main objectives is of course to present these complexities in a three-dimensional computerized model. Fractures they cross-cut, fractures they terminate against each other, they split, they show specific spacings, they are represented in swarms, they undulate, and they show openings, just as a few examples of these complexities. And in the end, we would like to represent these different relationships in a computerized model, for which we use the DMX protocol, which was introduced in 2019. So let's take a look at the different approaches that have been followed up to now in the modeling exercises. On the top of this diagram, we see data-driven approach, which basically uses the data set as has been observed, here an example, to just fit the fractures neatly around the observed information purely in a deterministic way, whereby, in this case, there will be no fractures or faults present outside the space where data have been observed. On the opposite side, the lower left of the diagram, we see the model-driven approach, which uses the statistical properties that has been observed from the data to fill a certain space with faults and fractures that respect these statistical properties in a purely probabilistic way. On the lower right side of the diagram, we have the process-driven approach, which starts with a clean, non-fractures or faulted rock and tries to mimic geomechanical and other processes to generate fractures and faults in space. An example of a combination of the model-driven and process-driven approach is this model where fractures are generated during the generation of a geological anticline. Now, the DMX protocol for the moment covers more or less this part of this diagram, providing the possibility of generating models with model data and specific process-driven approaches. The example we are going to discuss today is a combination of data and model-driven approaches, whereby we generate the fracture network using the data observed as seeds and filling the rest of the space with fractures following the statistical distributions as have been observed in the dataset. So let's take a look at the flow chart of the exercise which has to be performed. First of all, we have the FMX suite of tools, which looks at data like core, log, seismic, outcrop, satellite, remote sensing, any type of data set, extracts information from this data set, performs a series of analysis to take a look at length, height, size, shape, truncation distributions of the network and generates a conceptual geological model which describes all these parameters. From this we extract a series of function parameters and we define an input for the three-dimensional modeling in space. On the left, the input is the data themselves. We call this a codified trace map. We come back to this. And on the right side is the definition of the parameters for the different functions. Then we pass to the DMX Protocol, which performs the modeling space, extracts information from this model, and samples the model in the way that it can be combined with the data that were used as input. So we can extract the function parameters from this sample, make a confrontation, and so perform the modeling again until we have a best fit. So in the end, we extract from the three-dimensional model different parameters which are important for our processes in reservoir modeling, planning deviated wells, frac jobs, etc. Here we see a diagram that first of all describes what is the FMX protocol, which handles the analysis of the data regarding the fractures and the faults. Data can come from satellite, graph mark, seismic log, outcrop core, tin sections, anything that is important to characterize the reservoir. The parameters that are analyzed are the classical ones: orientation, length, height, the size, spacing, truncations, the most important parameters that characterize the fault and the fracture network. On the base of the diagram we see some outputs of the FPDM protocol, which was launched in the 90s, produces codified trace maps, density and orientation maps, domain maps, and can be also extended in 3D. All of this to extract a series of fundamental parameters to use as input for the DMX modeling. So here a short explanation of the DMX protocol, which is a tool developed over 25 years time span and launched in 2019, which is specialized in the modeling of a specific association of discontinuities, fractures and faults, as have been observed in nature, using the specific set of dependencies and relationships as have been observed in the data between the faults and the fractures, and between the faults and the fractures and the geological features present in the area. We see a list of specific new features of this tool. All kinds of fracture and fault shapes can be modeled, orientations, 3D truncations, algorithms, definitions of sets. We can model fracturing, erosional, deformational phasing, fracture spacing can be handled in different ways, branching, and fault slip control. So let's take a look at a number of specific features of the DMX protocol. Here we see a series of features which the protocol can handle for each single fracture that needs to be modeled. Therefore, for the fractures, we need, of course, information to be extracted on the dataset on all these different parameters, which can be summarized basically of where is a fracture and how is this fracture. So a position in the space can be a position linked to geological structures, shape, size, morphing, kinds of shapes it can have, apertures, and then on the other side the orientation of the feature in space, dynamic properties can be attached to the feature, and then on the right bottom all the dependencies of all these different parameters on geological structures. And in this diagram we try to summarize briefly how these dependencies work. On the left we see the properties of the single fractures, again position, shapes, morphing, aperture, orientations, and all kinds of different attributes. On the right side, the different type of dependencies that can be imagined. Can be dependencies on the other discontinuities in the model, so between the different sets or the different features, spacing, zoning, truncation, etc. Or it can be dependencies on geological features, like faults, different spatial variations, depending on the structure, etc. In the central box on the bottom, we have all types of probabilistic variations that can be applied both to the attributes of the fractures on the left or to the dependencies themselves. So in the middle, DMX Protocol manages all these dependencies during the modeling. So here we see some examples of how the outcome of the DMX protocol looks like. On the top left, we see a fault zone with fractures modeled according to slip dependencies. On the top right, unenchelon sigmoidal fractures inside two conjugate corridors. On the lower left, we see details of the unique truncation algorithms. And on the base right, we see a fold model where the fractures have been generated according to the folding process. Here an example of the output. In this case, a purely probabilistic model. A few damage zones are being modeled, 3 sets, and truncations are being applied. On the left, we see different visualizations of the model, more or less transparency or only the intersection between the features visualized to understand the 3D connectivity of the system. Top right, a pavement section through the model, and top bottom, the statistical variations of the features as have been observed on the model. And here an example of a model generated using the actual data as acquired from the pavement and the probabilistic variation in space away from the data to fill the model. This example comes from another paper that is presented in ADIPEC on the Wadi B dolomites of the Triassic series of Ras El Khaimah in the Emirates. You're welcome to assist to that presentation too. And this is another example of a combination of data-driven and model-driven fracture generation. In this case, a small pavement where we have the seeding along the traces observed on the pavement and the filling of the space with fractures using the probabilistic statistical models extracted. Then we come to a few conclusions. First of all, the combination of data and model-driven approach constitutes a major step forward in discrete fault and fracture network modeling. And it is presented here for the first time. We have seen this in the last 2 examples I showed. Secondly, both the FMX and the DMX, the data analysis and the modeling side of the system, have seen enormous leaps forward in the capabilities of the algorithms, which is of course linked to technology development in general. Third one, we are facing a few major challenges now for the near future. The integration of this modeling and analysis system with a machine learning and artificial intelligence approach. Secondly, of course, the application and the verification with even more subsurface data sets to understand how the impact of this system will be on reservoir modeling in general and all the other applications we can imagine. Well, thank you for your attention, and my gratitude goes to EAGE for the possibility to present this paper, and hope to see you next time.